Thank you for joining us today for the Achieving GPU Efficiency Breakthroughs, How to Maximize Utilization for AI Workloads and Kubernetes webinar. I'm excited to introduce Andrew Hillier, CTO, who will lead today's session. Andrew is going to take us through just a couple of slides, and then he's going to get right into demo. So it's going to be a great session as it's mostly focused right in the KubeX product itself. And with that, I'm going to pass the mic over to Andrew to get us started.
Thanks, Daniela. Let's just dive right in. And today, it's hopefully a great topic. It's something we unveiled a couple of weeks ago at KubeCon around our new AI optimization. And in spirit of KubeCon, I'm standing up like I'm giving you a booth demo. So we're going to keep it pretty interactive and go through it live. But first, just a couple of things. So what is KubeX? Well, it's automated resource optimization. It's, of course, AI-driven, like everything is. I'll talk about that in a bit. But not only is it AI-driven optimization, it optimizes AI workloads. I'll talk a lot about that. I'll talk a bit about Kubernetes. We also do cloud workloads. I won't get into that today. But really, it's resource optimization, and the hot topic now is optimizing AI. Let's talk for a minute about how it works, what we actually do. What the product does, it basically automates the setting of resources. And to do that, what we do is we pull in a lot of raw data. I'm going to talk about Kubernetes today, so GPUs running in Kubernetes environments, the node data, the GPU data, the underlying cloud data, and we take all that and we do machine learning on it to establish the patterns of utilization and the patterns of replication. So we build out some pretty sophisticated models of what's happening in these environments. I'll show you this live in a second. We use all that and chew on that with pretty deep analytics that have very deep policies to figure out exactly what to do with them as far as how we optimize the resources. And that kind of turns into several different actions. One is the optimizing the container configurations, the requests and the limits, and I'll talk about the GPU requests as well, but also optimizing the underlying infrastructure that's running on. And so the nodes that it's running on and the GPUs on those nodes, again, which is the focus of today. We do general Kubernetes as well, but again, if the Kubernetes is running AI workloads running on GPUs, of course, that can get very expensive and it's become a hot topic to optimize. Once we do that, we have an automation controller that can just make it happen. So really the whole idea is once you're comfortable with what is being recommended, turn on automation, it all automatically happens and you get savings and you also get risk reduction. And I'll talk a little bit about those things. Also, on top of all this is an AI agent. So we use machine learning in the core of what we do, and then it's all wrapped in an LLM that lets you interact with it. And if I have time today, I'll show a little bit of that. That was also unveiled 2 weeks ago. And so you can just start asking it questions like, what's my least efficient GPU? And it will answer that question. So if we have time, we'll pull up a bit of that. If not, we'd certainly love to connect with you after that if you want to see a deeper demo after the session. The idea of all this is that in these environments, in general, the resources being requested are usually much more than is being used. And this is kind of a symbolic representation, I'll show you a real one in a second, of a case where at the node level, the orange line is the requested resources, in this case CPU, and it's way higher than what's actually being used, which is the blue and gray lines showing the peaks. And we see this everywhere we go. And so the idea is that if you apply the policy and then turn on automation, the requests will come down and be in line with utilization, and the cost goes down. And the idea being that you can see the utilization go down, but what typically happens is you just run on fewer and fewer nodes. And so that's the key piece here. And what I want to talk about today is GPUs, because this actually happens for GPUs as well and can be extremely expensive. So with that, I'm going to cut out the slide deck here and go over to the demo. So what we're looking at is the product. And again, I'm going to go live without a net here. I'm looking at a system similar to what we demoed at KubeCon 2 weeks ago. I'll just do a little bit of orientation around Kubernetes itself, and then I'll talk about GPUs. So what we're looking at here is the container analysis in a Kubernetes environment. And there's containers, there's nodes, the automation controller down the left here, and also the underlying cloud infrastructure is running on. If it's in the cloud, is also analyzed and optimized. And in here, I'm looking at a Kubernetes environment with a whole bunch of clusters, and then a whole lot of results being shown here. The main ones being, I'm running an environment that has about $33,000 worth of spend on the Kubernetes environment, and we're saying that a third of that is waste. You can get rid of that by optimizing the various components, CPU, memory, and of course, GPU. And like I mentioned in the PowerPoint, what I'm going to do for a second here is go down to the node level, because that's where the spend really happens. So these are all the nodes, these are all the clusters, and the node groups and the nodes that they're running on. And I'm going to pick on an AKS cluster here for a second. You see here, there's an AKS cluster. Here's a node group called Agent Pool running on G4 DS V5s. And if you look down here, this is that problem I showed in PowerPoint happening in real life. So for these nodes, the requested resources are about 75% of the capacity of the nodes. I can blow that up. So we're requesting out a lot of capacity, but the actual utilization is under 10%. It's kind of tripping along between 5 and 10%. And so that is an indication that app teams are asking for too much, in this case, CPU. If I bring down the CPU requests, I can get that orange line down and probably run on half as many nodes. We're not using that much memory. The memory looks pretty good, but we're using a ton of CPU. We're not actually using it. We're allocating it out. And so this is a core case for just Kubernetes optimization in general. And if I go back up to the top view, and I'm just going to skip right over to what we call the histograms, I can visualize that. So these are all the containers and how big they are, or how small they are. I should say how too big they are. So if I look at this one that's highlighted here, the CPU requests in the containers are way too big. There are about 1,000 containers that are 5 times bigger than they need to be. And if I click on that, I'll see what they are. And so in this case, I've got a bunch of containers. Here's an analysis container with 30 replicas that has been given 4 CPUs, but it only needs about 1.5 CPUs. And I can see that down here, and I can fix that by bringing the request down. And that's kind of the key thing here, is that we're getting very accurate recommendations to chop down the resources being used. And I can simply automate that. I can go into that AKS cluster and say enable automation, and the automation controller will start taking these actions. And that's a whole topic into itself. There's policies that govern how that works. But the goal is, let's get these resources in line with utilization, so we're not wasting a ton of money, because in this environment, we are wasting a ton of money. So that's a really quick view of Kubernetes itself. We have other webcasts. We can probably link to them that kind of go through this whole thing in a little more detail. But finding the waste is a key thing. Also finding the risks. So in this environment, we have out of memory kills. We have CPU throttling. If I click on those, I'll also see the actions that will fix those problems. We see a lot of those problems in the field, and that can be automated as well. So for general Kubernetes, the idea is just fix the problems, bring the cost down, bring the risk down, and make the whole environment work better. The AI I'm showing is running on Kubernetes, but that's Kubernetes unto itself. Let's talk about AI workloads. So in this $33,000 a month spend, about almost half of it is GPUs. And that's what we're finding out there, is that GPUs are extremely expensive. So we have over 2,000, almost 3,000 containers running here, and 15 of them are running on GPUs, but they're about half the cost. And so that's why this is becoming such a hot topic. We have customers that have quite a lot of GPU infrastructure, and it also isn't well utilized. And to show that, I'm going to go back down to the nodes. So I'm going to go from containers back down to the nodes. And if I look through these node groups, I showed you this AKS cluster a minute ago. But if I go down here further, here's a EKS cluster and EKS clusters running on G5s. And if I look at the nodes, this is just running on one node, one G5 2XL. And now I can start to see the GPU utilization. So this is the bottom left curve is the GPU utilization. It isn't doing very much. It's sitting around 10 or 12%. The memory, even lower. It's barely using any memory. The power consumption, interestingly, is just tripping along, using a bunch of power, not really doing any work. So this is a pretty egregious example, but that's an example of a GPU node in a GPU node group that is underutilized and basically wasting money. And now this, again, seems like a pretty extreme example, but this is exactly what we see in the environments we analyze, where there are some GPUs that are well utilized and some are not well utilized. In one particular example of a pretty big environment, about 20% of the GPUs were utilized well, about 40% weren't even half utilized, and about another 40% were barely an eighth utilized. They were really low utilizations. We do see this in the field, and it's an expensive asset that we're just not using. And you see there's some other GPU clusters in here as well that are also not well utilized. This one's a little better. This one's running at about 50% utilization. This one not. It's not even hitting 50% utilization. Across the board, we see efficiency problems in the GPUs. So with that problem, the problem is I can't just go and start changing those nodes to be smaller nodes or whatever, because those nodes need to have enough GPU capacity to service what's being asked for at the container level. So for that, let's come back up to our container view, and I'm going to drill down on these 15 GPU workloads, these AI workloads running on GPUs, which are running on the nodes we just looked at. So this is really the heart of the subject today, is how do I drive higher efficiency in these environments? So we saw we have GPU nodes running out there. Here's all the containers that are running on those nodes. And it's kind of a single view across the whole environment. I can click in on different sections of the environment and see this view just for that section of the environment, or maybe just a business team or whatever that is. I'm just going to look at everything all at once. And let's just start at the top of this list. So this is an LLM running on an NVIDIA A100 80 gigabyte. And it's identifying a pretty big cost saving opportunity. And the reason why that is you see these curves at the bottom, this workload is not using the GPU very well. It's not even hitting a quarter of the GPU capacity. The request is 1 GPU. This container is asking for a GPU. It's never really even using a quarter of that GPU. And for memory, I can see the GPU memory of the busiest container in percentage is also just above 20% memory utilization. So this is a case where this thing isn't doing very much. Again, its power usage is chugging along at around 200 watts, but it's not actually using the GPU very well. And so because of that, what it's doing here is if I click on this link, it's actually recommending that I go to a quarter of that GPU. And it's running on an A100, and an A100 can be MIG. So MIG is multi-instance group. It means you can divide it up into as little as an eighth of a GPU. And this is saying, well, based on that utilization pattern, you're currently pretty low utilization. You could quadruple that utilization if you just put it on a slice of that GPU. And that's what it's recommending. It's recommending a 2G20 MIG. So this is key because this type of GPU can be sliced up. And so why run it on a whole one if you're not using it? Now, that's the recommendation. And so if I go and do that, I'm obviously going to run on less infrastructure. But I'll just drill down a little more into that and how we got that answer and what other alternatives I have. So to do that, I'm going to pull up this map. And this is new, and this is patent pending. It's one of the things we unveiled a couple of weeks ago. This is an analysis of that GPU workload across a wide variety of GPUs. So what should I be running it on? And just to explain this map, across the bottom are the GPU types. Let me just show you here. We've got a bunch on the far left are a bunch of AMDs, these Instincts and Radeons. I've got a bunch of NVIDIAs here. That's kind of the middle of the map, which are the common ones used. And I even have a couple of CPUs in here, some new Granite Rapids Xeon 6 CPUs, because we do get asked by customers, my workload, is it small enough that it'll just work on a CPU? Do I even need a GPU? And the answer in some cases is yes. So let's explore that. These are the GPUs across the bottom. The sizes are up the left. The one line is a whole GPU. And so this one is running on a whole A180 gig. Above that line are multiples. So if I'm running on 4 GPUs or 8 GPUs, that'll be reflected there. And below the line are the MIGs. So some GPUs can be divided up, some can't. So the A100 can be chopped down to as little as eighths. Over here, for example, a Tesla T4 can't be MIG. You can only run on one or more. And again, some of the AMD ones can also be chopped up into smaller pieces. So what this is telling us is that I'm currently running on a full one. I can fit on a quarter and be just fine. Would I fit on an eighth? If I click on that, at the bottom, it'll say, well, technically, you're okay, but it doesn't have enough GPU resources to do that. GPU or GPU memory resources. So I can actually explore around here and say, well, why not that one? Well, it's just not big enough. So a whole bunch of different ones are options here. You see this B200, I can even run on an eighth of that. That one's quite a bit faster, and that's a viable option, but it's more expensive than the one I'm on at a quarter. So that's a pretty expensive GPU. And so even though that would work and it fits, it's not financially as good as this one. So you can see I can kind of explore my options, say, what if, if I put it there, the red means you don't fit. The orange means there's a policy violation there. So why not go back onto, I don't know, an A10G? Well, you see here now there's a technical compatibility flag here saying you're losing NVLink. So maybe you don't want to go backwards. You can edit these policies and change them if you want, but we're saying, don't lose NVLink, don't go to older versions of CUDA. You see this one has an older version of CUDA. So, you can say don't do that, or you can say go ahead, you can lift those constraints if you want to. So the idea being we're going to explore all the different GPU options and figure out which one is the best. And in this case, I'm staying in the same model, I'm just chopping it up. So it's kind of a no-brainer. Why don't you just basically take the MIG recommendation and run it on a smaller slice of that GPU. Before I leave this, I also want to mention those CPUs, because you can see this one will actually fit on a 16-core Xeon. There is a technical compatibility flag here. That's why it's orange, because there is no CUDA support inherent in that platform. But if you lifted that constraint for a very small workload like this, that would work on a CPU as well. We get asked that quite a bit for ones that are just using a fraction of a small GPU. Do I even need a GPU for it? And this is an example where, yes, it'll fit, but there might be some technical issues with that. And for the bigger CPU, it would even fit on a quarter of that CPU. So we're getting all the different options here. Red means it won't fit. Orange means there's a compatibility violation, so you might not want to do it. Yellow means, yeah, it'll work, but it's pretty expensive, and it's what we call a spend tolerance. So I can say, only show me the options that are within 50% of my optimal. And now you see it kind of says, well, that one's the best. These ones are also options. They're not crazy from a price perspective, but this is still the best option. So we can use a spend tolerance to narrow down options to say, okay, this one's the best, this one's within 20%, so it's also decent. So that's what the spend tolerance is for up here, just to give us some kind of control over the cost of what I'm doing. That's a quick run through of one example here, an LLM, where I can save quite a bit of money by downsizing it. I'll show another example really quickly here. Here's a Tesla T4. So this is actually a pretty small GPU. We see quite a few of these out there, and they're pretty good because they're not very expensive. So this one's running on a T4, and it would also run a T4G. It's recommending a quarter of an A30 in this case. That would be the best thing to run it on. But unfortunately, if I go up here, this one's running in Amazon. That model isn't in Amazon. So the best one in Amazon is a T4G, which is the Graviton head node of a T4. So again, it understands the provider you're in. You can use it to analyze across providers, or just within your provider, or just within the same architecture. And one of the things that we're looking to do with this is not only model the big hyperscalers, but also the neoclouds. So for example, CoreWeave. We had meetings with CoreWeave, Crusoe, a couple of weeks ago, and we can also model these same ones available in a different provider and their costs, and you can say, okay, that might be a better option if you host it over there. So the idea being it can stay within the provider, or you can use it to assess across different providers. You can use it to basically generate MIG plans, like I showed in that first example. Let's divide it up, or let's MIG it up, or even just move to a different type. And the simple crash of all this is that all the ones that can be MIG'd, you see here it's dividing them up. These are all on individual GPUs right now. But if I add up the 2, 4, 2, I think it comes to, 2, 6, 8, 12 16ths of a GPU. So this will all fit on 2 GPUs if I divide them up this way. And so big efficiency gain by doing that. And all I need to do basically is, if I just set this as a request, this can all be done by the node autoscaler. So the node autoscaler can just turn on the right size MIG when this thing schedules up. It can actually be automated in a very elegant way. If it's on-prem, then you just want to divide them up. It just generates a plan to divide up your GPUs into the right configurations for the workloads to run on. So that savings can be realized fairly quickly. That's kind of all I wanted to cover today. I think I'm close to the end of the time here, but the idea being Kubernetes optimization in general is usually a big priority for companies. If you're running AI workloads in Kubernetes, which we see more and more of, especially inference workloads, then we're starting to see huge costs associated with GPUs and huge opportunity to automate the resource specifications of these GPUs to save an absolute ton of money. So with that, just to close it off, there's deeper topics we can get into, of course, like benchmarking. This is all using FP32. And if you're really interested, we'd be happy to have a deeper discussion around that, and get a deeper demo. So there's a couple of QR codes here if you want to do that. You can also just try this for yourself. We have a free trial. So you just install the Helm chart, you sign up, you get a Helm chart, it starts running against your environment. You run the DCGM exporter in your environment, and boom, you'll get these maps and this analysis. If you want to try it, go for it. And so these are the 2 options moving forward. And with that, I'll pass it back to Daniela.
So at this point, just like to thank everyone for their time. Thanks for joining, and we hope to see you at the next webinar. Thanks, Andrew.
Thanks, everyone.